In this example, we're going to go ahead and we're going to sketch this quadratic function. We can clearly see it's a quadratic. It's got a degree of 2, and therefore we know it's based on the parent function, which is just f at x equals x squared. Now, when I first look at this function here, I can see a couple of things right off the bat. I can see that there is a negative 1/2 in front of the function, and that means that, well, the negative is going to give me a reflection in the x-axis. It's going to open down instead of up. The 1/2 is a compression, so we are going to kind of be squishing the parabola vertically, so it's going to be compressed. If I look at the very end with the +4, well, that's a vertical translation, and we know that that's going to move the entire shape up by 4. All right, well, let's take a look inside where the x is. And this is give me a little bit of concern, because normally when we're taking a look and we're trying to pull out the stretch or compression, the horizontal reflection, or the horizontal translation, we want to see x all by itself inside the brackets. So if we were expecting to see this normally inside the squared, we would have just x all by itself, and then we'd be able to read off the p value, which is the actual, if you think of that, that's the axis of symmetry. That's the x coordinate of the vertex, or the horizontal translation. So that's where we're expecting to see. But if I look at this function here, I clearly don't see that. There's a problem because we've got this value of 2 associated with the x. Okay, it's being multiplied in there. So to get started, the first thing I'm going to do is I'm just going to manipulate the equation a little bit to help get that x all by itself. And we're just going to factor out that 2. So I'll just carry on here, and I'll just say, okay, so we've got 1/2, and then let's go ahead and factor out the 2. So we'll factor that out, and then what's remaining is x plus 3, and then all of that is still squared, and then we have the +4 at the end. Okay, so, well, if I rewrite this, we might be able to take it one more step and actually make things even a little simpler. So here's the f at x equals, and it'll be negative 1/2, and then that's going to be multiplied by, and I notice that I've got 2 times x plus 3, and both of them are squared. So that's like saying, all right, you've actually got a 2 that is squared, and an x plus 3 that is also squared. And then we've got +4. Okay? Well, you can see that by pulling out the 2 that is multiplied by this x plus 3 and squaring it, that we were able to kind of get the x all by itself. And we notice we can combine these together. So this is going to be quite simply f at x equals, and we know that 2 squared is 4, so that is going to be negative 4 over 2. And we're left with x plus 3 squared plus 4. A little bit of simplifying here gives us negative 2, and then x plus 3 squared plus 4. All right, so what started out as a, and if I look earlier in the equation here, you can see that when I was at this stage up here, I have a horizontal translation, and then I also have this red 2, and that is a horizontal compression. So remember, inside, when you're associated with the x, it's the opposite of what you would think. So that 2 looks like it's doubling everything in the x, and it looks like it would be a horizontal stretch. Well, it's not. It's the opposite. So it's a horizontal compression. Similarly, this x plus 3, you would normally associate a positive 3 value to imply that you're going to go to the right. But remember, it's opposite. If that says plus 3, it's actually x minus -3. So it is going to be moving to the left. Okay, so by factoring this out and pulling out this red 2, squaring it, and combining it with the vertical stretch, or in this case, it was a vertical compression, now we just have one stretch or compression. We just have the vertical one. We no longer have a value in front of the x inside. So this has actually reduced our work and made it pretty easy to do. So let's just summarize the transformations that we're going to be applying, and then we'll go ahead and sketch it. So -2, okay, well the negative is going to be a reflection in the x-axis, and this is now going to open down, and the 2 is a stretch. So it's going to be a vertical stretch downward by a factor of 2. All right, if we take a look at the other transformations, we have a horizontal translation, and it's going to be going to the left 3, remember, opposite, and a vertical translation up by 4, positive 4. Okay, so we just have 3 little translations, or rather transformations, to do to the parent function, and then we should have our new sketch. So to get started, why don't we go and place the original parent function on the grid, and then we'll be able to show how we get the new function and its relationship. So the parent function, if you remember, f at x equals x squared is a parabola. It is centered at the origin. Okay, so I'll just put a dot right there at the origin. And then the stepping pattern is over 1 and up 1, over 1 and up 1, 2, 3, and it does the same on the other side, over 1, up 1, 2, 3, just like that. And if I was to, go ahead and sketch this, I would see that this is the sort of the general shape of the parent function y equals x squared. Okay, well, how about our transformed function? Well, again, let's first start by figuring out where we should begin sketching this. And in the transform function, the first point that I'm going to always sketch is going to be the vertex. And I want you to think of that as the anchor point of this function. So the vertex used to be at 0, 0. But given that this is now vertex form, we can clearly see that the vertex has been moved to the left 3 and up 4. Okay, so let's do that. We're going to go to the left 3, 1, 2, 3, and up 4, 1, 2, 3, 4, and right there, excuse me, is where the vertex is. So that's where we're starting, where that red dot is. Okay, now we can just apply these, in this case, vertical stretch down, and we do not have a horizontal stretch or compression. We actually removed it out of the function and we put it out front. So this turns into a pretty straightforward exercise. We're going to go ahead and we're just going to start at the vertex. We're going to be moving down, and the stepping pattern is over 1 and down 2 instead of down 1, and then over 1, and normally we would go down 3. In this case, we'll go down 6. So 1, 2, 3, 4, 5, 6 to there. We have a symmetrical set of points on the other side of the axis symmetry. And so if I was just to connect those up and give them a little bit of a sketch, we've got kind of, well, that wasn't very good. Let's start here and go down. And that was even worse. All right, that looks there, not too bad. Okay. So there's the actual transform function. Okay. Now, well, what if we hadn't pulled out this 2? So what if we were in the situation where we were working with a function and we couldn't actually pull out this horizontal, in this case, compression? Would we still get the same function. And well, what we're going to do is we're going to walk through this, and I'm going to show you that yes, in fact, you would. And we'll go through and we're going to work from this version of the function right here. Okay, and we're going to convince ourselves that in fact if we had left the 2 in there, we could still apply the exact same transformations and get the exact same function. Okay, all right. So let's go ahead and start. The vertex is still going to be at -3, +4. So I would go to -3, 1, 2, 3, and up to 4, and I would go ahead and I would put a dot right there. Okay? I don't know if you can see that. Maybe, well, blue's fine. Maybe the black. Let's try that. That's a little better. Okay. So there's the starting point. Well, all right. Normally, we would go over 1 and down 1. Well, these values are different. We got -1/2 and a 2 here. So let's just take this one at a time, okay? So normally we would go over 1. Exactly. This is a positive value, so we haven't changed anything, okay? We haven't reflected it in the y-axis. We do have a 2 here, however, and that 2 is a horizontal compression. So if we normally would have gone over 1, now we're only allowed to go over 1/2. Okay, so I'm going to go over 1/2 and then worry about going down now. Now, the parent function, if you go over 1, the first step is over 1 and up 1. So we should go over 1/2 and then down 1. But now I look up here and I realize that there is a vertical compression. Remember, inside is opposite. So this looks like a stretch, it's a compression. Outside, it is the way it appears. 1/2, that's a compression. So the first step is actually over 1/2 and down 1/2. And I'm just going to put a dot right there and there. And it looks like we're still on the graph. Okay, let's take another step. So from there, in the parent function, the normal stepping pattern would have been over 1, down 3. Okay, but it's not. We have a horizontal compression. So instead of over 1, I'm only allowed to go over 1/2. Normally I would go then down 3. I can't go down 3 because there is a vertical compression of 1/2 as well. So instead of going down 3, I'm only allowed to go down 1.5, or 3 steps of 1/2. So I'm going to go over 1/2 and down 1 step of 1/2, 2 steps of 1/2, 3 steps of 1/2. And there's the dot. And I'll put the same one on the other side. So you can clearly see that even if I had performed the horizontal compression and the vertical compression separately, instead of factoring out that 2 and then combining it at the front, I would get the exact same shape, the exact same function. Okay? Well, what if you wanted to use a table of values? Again, we would just set up an x and a y. I'm just going to make the pen a little, there we go. And we'd put in some initial points. And I'm just going to do 3 points just to show you. So the original parent function would be -1 and 1, 0, 0, there's the vertex, and then +1 and +1. Okay, let's use this last function here, right here, and we're going to take this and we're going to apply those transformations into this table of values. Okay, so let's work with the x first. We do not have a stretch or a compression or a reflection in the x, but we do have a red translation to the left by 3. So I'm going to take the x values and I'm going to subtract 3 from all the x values. -1 subtract 3 is -4. That is -3. And 1 subtract 3 is -2. So those are my x values. The y values, well, they need to change as well. we're going to apply that red, or sorry, the blue, vertical stretch of 2. And I'm also going to apply the negative, which is going to mirror or reflect the parabola. So it opens down. I'm going to reflect it in the x-axis. So I'm going to take this y value and I'm going to multiply everything by -2. And that leads me to 1 times -2 is -2. 0 times -2 is 0. And 1 times -2 is -2. Okay. Last but not least, the vertical translation up of 4. So I'm going to take the red 4 and I'm going to add 4 to all of these values. So -2 plus 4 is +2. 0 plus 4 is 4. And -2 plus 4 is +2. That means that this mirror, or this new function that is the transformed parent function, should have 3 points at, and I'll just put them sideways so they fit, -4 and +2, -3 and +4, and -2 and +2. And if I go up to my function and I take a look at it, well, -4 and +2, -1, 2, 3, 4, and up 1, 2. That's that point right there. Check, that is on the function. -3, +4, 1, 2, 3, and up 1, 2, 3, 4. That's that vertex point there. And last but not least, -2 and +2, 1, 2, negative, up 2, there it is there, and that's the third point. So you can see that there's a number of different ways to tackle this. We could have just pulled the 2 out with factoring and then left it alone and applied that horizontal compression, or we take the one more step and we take that out, combine it in the front with the vertical direction, and now we've just got a single vertical stretch. We can always check our work with a table of values, and that's about it. There's the original function, x squared, and then there's the transform function.